Good morning everyone. Now I would like to discuss some previous question papers about the mathematics 1. It is the R-13. For the student request, I am going to discuss this paper R-13 one by one. It has two parts. One is part A and part B. Part A carries 25 marks. In that, the first question is define elementary matrix with an example. It carries 2 marks. 2 marks with example carries 1 mark and definition is 1 mark. Okay. The definition of the elementary matrix with an example means the set of elements a system has mn numbers. Those numbers are either real or complex. Can be arranged in a ordered set m rows. Each row constituting ordered set or ordered pair of or ordered set of n numbers. Can be either square brackets or open brackets or non brackets. Is called elementary matrix or elements of a matrix. Elementary matrix. Or simply we can define the set of mn elements can be arranged. Mn elements can be arranged in m rows, each row containing n elements as a column. Then this arrangement is called elementary matrix. Elementary matrix. It can be expressed in the form of, or it can be arranged in square brackets or open brackets or double line brackets or normed vectors. It is simply denoted by capital A equal to A11, A12, so on A1n, A21, A22, so on A2n, so on A M1, A M2, so on A Mn. It is simply can be written as Aij with m by n matrix, where 1 is less than, I is less than or equal to m, and 1 is less than, j is less than or equal to n. It is nothing but The elements, mn number of elements can be arranged in m rows and also in columns. That arrangement is can be equipped with either square brackets or open brackets or double line or non brackets. In this, simply it can be denoted by aij m by n. Here I element is equal to I, 1 is less than or equal to I is less than or equal to m, 1 is less than or equal to j is less than or equal to n. Suppose we can take one example. That example is A is a 3 by 3 matrix. Then we can take 1, 1, 1, 2, 3, 4, 5, 6, 5. It is a one example of element matrix. It has 9 elements. These can be arranged in n 3 rows and 3 columns. It is called as a square matrix. This is a 3 by 3 matrix. And one more example, 2 rows with the 3 columns. Then that is 1, 2, 3, 1, 0, 5. It is the 2 by 3 matrix. You can take any example. Okay. Next, B bit. Prove that an orthogonal set of vectors is linearly independent. Second one. Prove that an orthogonal set of vectors is linearly independent. It is a 3 marks question. In this, first, what is the linearly independent condition? Let x1, x2, x1, xn are non-zero vectors and a1, a2, so on, an are scalars. If the linear combination of scalar and vectors is equal to 0. That is nothing but a1 x1 plus a2 x2 plus so on plus an xn equal to 0. In this, then a1 equal to a2 equal to so on equal to an equal to 0. Therefore, x1, x2, so on, xn are linearly independent vectors. This is the condition or definition of the linearly independent. Here, simply we can prove that in the linear combination of the vectors and scalars, we can prove all scalars must be equal to 0. Then the given vectors are linearly independent vectors. Here what they are asking, prove that an orthogonal set of vectors. Let P is equal to set of E1, E2, so on, En are orthogonal vectors. These are orthogonal. En is an orthogonal set. Okay, where E1 equal to x1 by mod x1, E2 equal to x2 by mod x2, so on En equal to xn by mod xn or norm xn. Here E1, E2, so on En are the identity vectors. Why? Because these normal vectors means orthonormal vectors means those normal condition, orthonormal condition, even by modulus of or norm of x1 is the identity element or identity vector. Here P is equal to set of E1, E2, so on En is an orthogonal set means in that individual vectors what are the elements are, those elements are satisfies the condition of the orthogonal. Orthogonal means x1 by norm x1, then that is called as orthogonal set of vectors. Okay, here in this E1, E2, so on En are non-zero orthogonal set or non-zero orthogonal vectors. Here we can take the linear combination with the scalars a1, a2, so on an is a1 e1 plus a2 e2 plus so on plus an en is equal to 0. Clearly here e1, e2, so on en are orthogonal vectors. Those are called orthogonal vectors. Orthogonal vectors means those satisfies the relation x1 by norm x1. It is clearly equal to 1. Here E1, E2, so on En are E1, E2, so on En are non-zero vectors. These are non-zero vectors. If in the combination of the linear combination, if no one vector is a non-zero vector means compulsory the scalar should be equal to 0. So on an equal to 0. If all scalars should be equal to 0, then the P set, what we can take the orthogonal set, that is clearly linearly independent set. Therefore, P equal to set of E1, E2, so on En is an orthogonal set is linearly independent. This is the proof of how we can take the linearly independent. Prove that an orthogonal set of vectors is linearly independent. First, they have given the 1 mark for the linearly independent definition. Next, that in the construction of the orthogonal set, the each and every element can satisfies the relation of the orthonormal, that is orthogonal condition. In the orthogonal condition, the elements are non-zero elements. Why? Because the orthogonal condition is E1 equal to x1 by norm x1. It is equal to 1. Okay. In that case, these all are non-zero vectors. Then the combination with the how many vectors we can take in the orthonormal set, then that is equal to, then the combination of those vectors and scalars are equal to 0. This is the condition for the linear independent. In that we can prove that each and every scalar, how many we are taking the scalars with the combination of these vectors, those scalars should be equal to 0. Here clearly E1 to En are non-zero vectors. Then when we can multiply those vectors with the 0 scalars, then it is equal to 0. So a1, a2, so on an is equal to 0. So all scalars equal to 0. Then what we can take the orthogonal set with the n vectors, then that is clearly linearly independent set. Okay, next C. Okay, it is these two problems in the matrix chapter. Next C and D are also in the relation of the linearly dependent, functionally dependent and stationary points we can find out. It can be discussed in the next class. Okay, thank you. If you like this video, please subscribe my channel and share to your friends.